All right. Yeah, Calvin, what's up?
I noticed that the ones due tomorrow are actually due at 4:30 a.m.
Yeah, you emailed me about that. Sorry, I'm not going to change that. They're actually due PM. Now, just try to get them done today if you can. That's my bad. Yeah, Ellie's laughing at me. She's like, Mr. Hudson doesn't know AM versus PM. I just Khan Academy defaulted when I typed 4:30 and then hit enter. I thought it was going to default to PM because that's what I keep assigning, but it defaulted to AM. So sorry, that's just my bad. I'm not going to go change it, but I'm not going to count things late if you do them tomorrow. I probably won't update grades in map until next week, if we're being honest. Like, I don't really do a lot online over the weekend. I do paper grading when I have that stuff to do. So we had been talking about exponential expressions and equations. We're going to do one final review about those things. But now today we're going to start talking about interpreting exponential models. So let's go ahead and dive into what is it that we're talking about today. I'm screen sharing, right? I'm expecting that you guys should be rolling on the floor laughing like, ah ha ha, it's a joke about dating, but it's a play on words because dating, like, go on a dinner date versus dating, like, how old is something? Ha cha 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 cha. Hey, there's Amar. Guys, they missed the joke. Amar and Aaron are late, and now they missed the joke. All right, guys, you're late. So, Aaron, Amar, next time in class, next Tuesday, you need to be here early by 9:55, okay? You got to show me that you can be here early. Email me if there was some sort of tech issue or something that happened this morning, but you're late, right? You're tardy. So, here's our start slide. It's in the video that will go up on YouTube, so you can go watch that if you want. We have some spread out due dates, so go check your Khan Academy. We've got due dates of the 4th, the 8th, and the 14th, but we got to dive in because we were kind of wasting time waiting for you guys. So, and if Creative Start keeps you late, leave. They only have so long, right? They got to end class when they got to end class, same as me. So, this is a joke. We're going to get, by the end of our lesson, to the point of why do we talk about carbon when we're trying to figure out how old things are. So really quickly, we wanted to review a couple more problems like this before we move on. So go ahead and write these down on your paper. We are going to try to remember what we do with these things. So the first one and the last one are probably the most awkward here. With radical 98 divided by 2 to the 1/2, what would we actually do there? Anyone want to unmute and help me out? You can just unmute and start talking. Yeah, go ahead, Margaret. Yeah, so you took 2 to the 1/2 power and you just rewrote it, is really what you did. Is you rewrote it as square root of 2. All right, what next? Oh, so we're allowed to then put them together like this? Sweet. This is really just to review some rules, guys. We're just doing like one more rules review before we move on. All right, so Margaret, what'd you do then? And that is 49. And what's the radical 49? 7, right? So we could say positive or negative 7. Or if you just use the primary root, we would just say positive 7. Right? So remember, the positive is the primary root. The positive or the negative is both roots. So then, can somebody not Margaret tell me what to do with the next one of the 4th root of 2 divided by the 4th root of 162? We can kind of take what Margaret just did and use that to help us solve the next problem, potentially.
I did it a little bit different than what Margaret did last time.
All right, Kaylin, well, tell me how you did it.
Since both of them technically equal, like 2 to the 1/4 and 162 to the 1/4, I changed it to 2 over 162 to
Same thing that Margaret did with like rewriting. You just went the other way, right? So instead of going into root form or radical form, you went into exponent form. Totally fine. What'd you do from there?
And then I just simplified it to 1 over 81. And then it was just that to the 1/4, which I got 1/3.
Yeah, because 81 has a nice fourth root. So the fourth root of 81 is 3. The fourth root of 1 is 3. Now, guys, this is the same as writing the fourth root of 1 over the fourth root of 81. Or really what we would have gotten to here is the fourth root of 1 over 81, which either way, it's all the same. It comes out to be 1/3. Put in parentheses, or you don't have to. I'm going to scooch my screen. We'll go right there. Somebody not Margaret or Kaylin. Somebody else who can help me with the next one. Do the rules work the same with multiplication as they do division? Ooh, we add the exponents, right? Because when we're multiplying... Now, what lets us be allowed to add the exponents, Avi? The same base. So since we have the same base, I can never make my 8s look very good. I'm sorry, guys. I'll just apologize right now for all the times that my 8s look crappy. So negative... Oh, crap. Well, 1/2 is really 2/4. 2/4 minus 3/4. Negative 1/4? Somebody correct me if I'm wrong. Yeah? So, Avi, since you volunteered for this question, what's the negative in the power tell me to do?
Have the reciprocal
of the excuse me, of the base, right? So reciprocal of the base. So we flip this over, and 81 over 1 doesn't really need that 1 on the bottom. The negative's gone now. Oh. So, wait, then it's just 81 to the 1/4 I could rewrite as... Well, we don't really have to if we listen to what Kaylin said last time. Yeah, we could rewrite it like this. But, Avi, would Kaylin tell us the fourth root of 81 is? 3. Boom. Answer's 3. So in the last one over here, we have 3 to the 1/5. That's a 4. Over the 5th root of negative 96. Take a moment to do this on your own. Everybody. Reminds me of the Backstreet Boys. Do this on your own. You guys probably don't even know who the Backstreet Boys are. Question here is going to be, is this one going to only have one answer? Or are there going to be multiple answers? And what is that? Oh, okay. That works out. Katie Ann, is that a hand? Well, it is a hand, but is that a hand raised? So you said you think it's negative 1/2. Sorry, I missed what you said after that. I like that you're not sure about the second number, because it's wrong. So that's why your brain was saying, do we have both of these here? Odd roots, right? Odd roots are allowed to take the roots of negatives. Even roots are going to need to involve imaginary numbers, right? But odd roots will say, if I do negative 1/2 times itself 4 more times, right? 5 times in total, I'll get negative 1/32. This is our only answer. There are not multiple answers here. Does that make sense? Sweet. So I'm glad that you were second guessing yourself there. What questions still remain from any of these four that we used as our review to start today's lesson? All right, we're moving in then. Moving in, moving on. I don't know what we're doing. So exponential models. Guys, I want you to take a moment to read this problem while I'm just quiet. Then, once you've read it, go ahead and write down exponential models. If you did not date your paper yet, please date it. I have a date up top, but I'm going to go ahead and write the date here again. I'm trying to start keeping all my notes in one notebook to keep myself a little better organized instead of using loose graph paper. So actually, hopefully you'll see this red and white graph paper. I also think the focus works a little better for my camera. So the exponential model they give to us here is L as a function of t, right? So L of t is how we say that quickly, is 750 times the quantity 1.85 to the t. Now, does anyone want to be bold? Sorry. I decided to make my one a little fatter because that decimal was too close to it. Anyone want to be bold and explain to us what they think this is saying in reference to the situation? Alina? What do we know for sure? Let's start there. Yes, yeah. Now wait, did the problem tell us that?
Sorry, what?
Did the problem tell us that? I'm not saying you're wrong, but did the problem... The equation did. Okay, so we're going to talk about how we know that, right? I agree with you. You're right, but everyone else like in the room may not understand how you figured that out. What's the problem tell us? What do we know for sure? What do the variables mean?
Oh, T is time or days, and then L is the number of locusts of is the output of time. Like over how much time does how many locusts?
Yeah, like locusts after T days, we could say. Here's the only problem with me using this notebook. I'm now stuck. I can't push it any further because my my penalty box that I have wrapped around here, right? So I got to move my camera. All right. So, guys, is anyone confused? We're going to build this slowly because some of us haven't seen exponentials before. Is anyone confused at why we wrote down that T is time in days and L of T is locus? Really, we just wrote that down because that's what the problem told us. This is called wait time. Trying to see if anyone's got questions. All right, so if we know that t is time in days, let's start playing with this function, right? What if we want to go to day 1. Well, if we want to go to day 1, well, actually not day 1, let's go to the beginning. What do we call the beginning of a situation? Like, if a story starts and says, like, the princess is in the castle, or whatever, what day is that?
Day 0?
Yeah! We actually would call that day 0. Because when something starts, it has not had any time elapsed. So please pay attention that T is time elapsed. It's time that has passed. So this is time elapsed. Please make sure that we write down that important detail, that T is time elapsed. So if we want to look at day 0, that's our beginning, right? That's when the situation started. And if we want to look at day 0, that turns our function into L of 0 equals 750 times 1.85 to the 0. Now this is where this gets fun. What is any number to the 0 power? Yeah, I got a few. 1, right? So if this is 1, then what does multiplying by 1 do? We got to create some like Zoom sign language. I mean, you can also just reach down and hit your space bar, but we need like some sign language for nothing.
Multiplying by 1 just keeps the number the same.
Yeah, it keeps it the same. It changes nothing. So on day 0, when this starts, there are 750 locusts. Now, I forget if we've seen the documentary in here, not talking about how locusts have all kinds of different broods, and they come out trying to avoid each other because they actually kill each other. Like the different broods of locusts, they either fight against each other and or it's just more dangerous for more of them to be out at the same time because then animals eat them all. Animals like to eat locusts because they're sweet, too. They taste sweet. Yeah, I know. Weird things you didn't want to know. Miss Allie, who's not here today, keeps saying that I am like the master of giving information that nobody asked for. She's like, I didn't ask to know that. And I'm like, I don't care. I have information I can impart on you. So what then? So 750 we can call our initial value. Okay, sweet. What then is the 1.85 there? Yeah, it's the growth or decay factor. So, is our locust population increasing or decreasing here? Just unmute. Yeah, we're increasing, right? So we're in, now wait, what could we say then? So our population is increasing. Who can finish that sentence?
By a factor of 1.85?
Yeah. But if we want to actually, like, that's the mathy, like, that's what we can, like, type into a calculator. But how could I talk about tomorrow versus today? Tomorrow will have... Well, yeah, let's not say almost. We're beyond saying things like almost. What percent did our population go up by?
5%.
Yeah, so our population is increasing by 85% daily. So, in general... Sorry, does anyone still need to see that? I'm going to rewrite that problem here in a minute. But so, in general, our exponential models are going to be in the form, what's our most common function notation? I was like, you already wrote it. I already saw it. F, right? F of x is going to equal a times b to the x. Now, I think we talked about this previously, but now we actually care about it, where a is the initial value. So really, when x is 0, right? A is the value when x is 0. B is our growth or decay factor. Growth if it's over 1, decay if it's less than 1. And x is time, but it's time based on the problem. So it might be seconds or minutes or days or weeks or months. So after time here, I'm just going to put caution. Because do not fall into the trap of thinking your exponent is always days or your exponent is always years. You got to be careful for that specific situation. So guys, that's the trap door in these situations. Does that make sense? So then, to make sure that we understand what we're doing here, and you're probably still on the same page because I write bigger than you guys, if our function was L of t equals 750 times 1.85 to the t, where t is days, right? Let's make a little table. Let's say L of t. And guys, we're going to do this because later you're going to be asked to do this backwards. So please do this with me, even if you're like, this is silly. I don't need to do this. I understand it. T is days. I had water. There's water. Build this table to show me the first week. What happens to the amount of locusts in the first week? Don't just jump to day 7. Let's build it for each day. And if you're like me, this is going to gross you out. I don't really like locusts. My sister used to like get the shells and like put them on me without me knowing. And then I'd like just find a shell on me and it was not fun. So, oh man, okay. So I'm going to flip my table around. Really, if X is our input, or if T is our input, I'd rather talk about T on the left part of my table. So I'm going to ignore this part. We're going to say T is 0, or T is 1, or T is 2, or T is 3, 4, 5, 6, 7. So we said on day 0, we have 750 locusts. What do we do to get to day 1?
Multiply by 1.85.
Get your calculator out if you have it. I'm going to show you a sweet trick here. So check it. The amount of locusts on day 1 is going to be 1387.5. So obviously there's a little bit of like the math has made it work, but you're not really going to have a half locust. It might be like half emerged. Check this. If I hit enter again, it repeats what I just did. So if I hit times 1.85, I grab the previous answer and multiply by 1.85. But guys, check this out. Now if I hit enter again, it grabs the previous answer, which is now 2566, multiplies by 1.85 again, and now my values are going to change as I go. So I can just keep hitting enter to get my new values instead of having to type in times 1.85 again. So this is a cool way that we can kind of shortcut using our calculator. So 2566. And guys, in our table, we can just go ahead and write down the whole numbers if you want. So day 3, 47, 48. Enter again. Enter again. Enter again. Oh my gosh. How many locusts are, that comma shouldn't be there. I'm sorry. How many locusts is there after a week? Are there? Sorry, that was bad grammar.
Too many.
I'm not hitting enter again. I'm just going to move my calculator. How about that?
55,625.
Yeah, gross. Gross, gross, gross. Guys, in a week.
That's why I said too many.
In
Way too many.
1 week. 7 days. We went from 750 to 55,000. I like feel them on me. So,
How they actually grow? Is this how fast they actually grow?
a certain, like, normally this data is like real from a situation that they've talked about. Now, sometimes they make up a new problem with new numbers, like just to use the same type of problem. So you might see another one in your homework where the locusts are decreasing because it's getting colder. So instead of like in the spring when they all are coming out, and literally guys, they like hibernate in the ground. So when they come out, there's like an exponential increase, but this may not stay true long term, right? This exponential model may only be true for the first 5 days, or maybe only true for the first 3 days. So remember, we start to give like domain restrictions. So we might come up to this function and say when, right, like after the function, we would say when like x is less than 5 or x is less than 2 or something like that. But when they emerge, that function models the behavior. So what we see here is every time we move forward, we multiply by 1.85. So guys, what if we had to determine what this was? What if we had to find the growth factor? How do we find the growth or decay factor? What math could we do to do that?
If we knew multiple of like, I'm just gonna call them points that would end up being on a graph, we could use that to figure it out.
What math are we going to do? Add, subtract, multiply, divide, because when we did linear equations, we were using subtraction, right? y2 minus y1, x2 minus x1.
So we would divide one number, bigger number by a smaller number?
You just said it. It was the second word you said. You divide, right? We divide to find the growth factor. And we'll talk more specifically about what exact divisions. But if we were solving this problem backwards, and they gave you on day 3, there were 4,748 locusts. On day 4, there were 8,785. You know that's a 1-day growth. So we could do 8785 divided by 4748. 1.85 is our growth factor. Now, what if... I don't know what that is. Oh, Omar must have dropped out. What if they didn't give you neighboring days? What if they gave you day 4 and day 1?
use the same process, but then you would divide the number that you got by the distance of the place.
So if we do the 87, let's test this. 8785 divided by 1387. Divide that by what? 3? 4. So we do minus over here.
3, I think.
So if we did 4 minus 1, that doesn't work. Or it didn't work, at least. What if we did 8785 divided by 1387 and then divide? No, we did divide. Divided by 4? That still doesn't work. All right, we might have to come back to this, right? What would we do? How can we deal with a situation that doesn't give us neighboring days, right? If it gives us neighboring days, like day 3, day 4, that's fine. We can just do the division. We'll come back to a situation. Nope. Sorry, Alina. We're moving on. Good thing you're muted. You're probably like swearing at me. Con, flab it, darn daggit. Mr. Hudson, rah, rah, rah. All right, try this. When Mustafa threw a beach ball to his friend, its horizontal velocity. Ooh, I'd be remiss if I didn't show. Have I shown you guys this shirt yet? Okay, I'm wearing my Velociraptor shirt. It's velocity of a raptor. So the velocity changed as it traveled through the air. The relationship between the elapsed time t. Ooh, what's time in here? What's time in here? Seconds, because this is a short-term event. That it doesn't last very long. Is this growth or decay? Decay. Katie Ann, thank you for unmuting. I was about to start picking on people I haven't really heard from today. Why? Can you explain what's happening in this situation in like simple terms? Yeah, we threw a ball and it's slowing down, right? So you said it's decreasing by 19% every second. So what we really want to look at here is, okay, so every second, blank percent of the so Katie Ann already told us that answer. 19% of the velocity would be subtracted? Sorry, I gotta send attendance, I just realized. Give me a second. If we lose 19%, is that subtracted or divided? Let's build a quick...
Because it's in, like, percentage form. Because it's not 0.81. If you did 0.81, it'd be factored. So that would be divided.
Yeah, so if we write this down, let's just for a quick little example in our notes. V of t was 4 times 0.81 to the t. So we know this is decay. You guys told me. Decay, we're losing 19%. And the velocity here is measured in centimeters per second. So if we did seconds... Hey guys, tell me when the ball stops. Why don't you try that? Figure out when the ball stops. So our initial value, whenever our input is 0, we'll get our initial value as the output. You tell me. So what you're saying here is mathematically the ball never stops. Like, so what if I go to a t of like a minute, right? Like a minute after this situation happened. Well, that'd be 4 times 0.81 to the power of 60. That gives me 1.29 times 10 to the negative 5th. So at some point, this situation doesn't make sense anymore. That's what we say, like, simply put, and I don't want you to think this is easy, but the simplest way we can say this is at some point, this stops making sense. Because if we consult with Desmos, we could look at this and say that y, right, our f of t, equals 4 times 0.81 to the x. Now, this is not dramatic because the ball doesn't slow down crazy fast. But, yeah, we can keep going out forever. And technically, we're still not at 0. Right? We have to keep zooming in. We're so close to 0 that the amount of accuracy we have to zoom into is kind of ridiculous. But now I went further than a minute, but right, 72 seconds in, we're still not as... So at some point, this doesn't make sense, right? Does it make sense to you that exponential models represent in a certain like moment or time span, but won't necessarily continue forever? Does that make sense to us, that like this is the model for the moment? So a lot of times we'll have some domain restrictions on things. So same thing right here, right? I just wanted to show this as, is this decay or growth? Decay. Whose ball's slowing down faster? Mustafa's or Zakir? Whose ball's slowing down fast? They both hit at the same speed. Whose ball's slowing down faster? Zakir, right? Now, if we modeled that in Desmos, we would see that they would both have the same y-intercept, and then Zakir's line would get below Mustafa's because it goes down faster. It has a lower value here, closer to 0, right? That's why it decays faster. Do we need to talk about, like, are we comfortable with this model of exponential? So is this growth or decay? Guys, some of you don't even reach for your spacebar. You're like, somebody else will answer. And they did. But yeah, decay, right? This is decay because it's less than 1. Growth or decay? Growth. How much does it grow by each day?
53%.
Yeah, don't fall in the trapdoor of saying 153. It's a growth of 53% each day. I think Amar is having some issues with his internet. So, read this for a moment. This is a different situation, right? I want you guys to take a moment to kind of dissect what does this mean? And this is where we're going to like end for today. Like we're going to talk about this and then we'll wrap up class. I'm going to drink some more coffee while you read that. Would anyone like to talk to me about what you think this situation means? I would prefer someone I haven't really talked with today. So maybe like Calvin, or I've heard from Aaron a little bit. Ellie, haven't really heard from you much. It's okay, I'm just looking to hear from somebody I haven't heard from. So there's a bacteria, right? What's happening with this bacteria? Is it going up or going down? Wow, guys, you really don't want to get out of class, do you? Katie Ann? Okay, tell me how. How is it decreasing? It's being cut in half, yes. Actually, let's make sure that we have this written down. So if you didn't write it down yet, because I didn't write it down yet, and I'm going to squeeze it into the same page here. I probably shouldn't use red since my graph paper's red. We have n of t. This is supposed to be purple, but it looks red. 1,000. 1,000 what? What are they talking about? I don't know, bacteria. It just, like, whatever unit they're talking about bacteria in, it starts at 1,000 times 1/2. Ooh, this is where it gets weird. T over 5.5. Man, I might even write this in blue because that purple or whatever pen isn't working very well. We start with 1,000. We're being cut in half. Who can tell me what you think this means? L?
Maybe for only a portion of the day, whatever's causing it happens.
Okay. Tell me more.
That was mainly a guess, so.
That's why I was saying tell me more. So just thank you for saying that, because that's, you know, I appreciate that we're all honest with each other. Alina?
I think it's every 5.5 seconds it halves, because if t is 5.5 divided by 5.5 is 1, so
We know this point. Alina's absolutely right. We know that this starts at 1,000. But when t is 1, the power would actually be 1 over 5.5. Amar, no worries, dude. I got this lesson recording, so I can tell you're having some tech issues, but I got it recording. It'll go up on YouTube later. So in order to actually make the multiplication or the decrease of 1/2 happen, our input has to be 5.5. So what this is telling us is the bacteria is cut in half. There's a V in that word. The English language is dumb. Bacteria is halved every 5.5. What's time in this situation? Seconds. Whoa, that's some fast medicine, right? In 5.5 seconds, it cut the bacteria in half. Now, the question I will end you with is, if I leave school right now and tell you every 3 minutes, I can get halfway home, when am I going to get home? Never, right? Technically, mathematically, if I start a trip and go halfway and halfway and halfway and I will never get home. But do you think a certain amount of bacteria is probably like okay, like our body can deal with it? Yeah. So the point of this, yeah, so the point of this is not to completely get rid of it, because obviously, mathematically at least, that can't happen, quote unquote. But the point of this is to reduce it so much so that it will be like indetectable or so small that it just doesn't matter. Does anyone have any remaining questions from today about exponential models? All right. Well, like I said, I got some due dates spread out for you guys because I'm hoping that if we all get our homework done by those due dates, I can use the feedback from those assignments to plan our class lessons. I want to start trying to be really efficient, so you'll notice I did not assign videos. If you choose to go watch the videos, that's up to you, but I am solving problems exactly like what you would see in the video. So I want you to be efficient with your time now that you're in school every day, right? So I'm not going to make you watch Khan Academy videos if you don't need to. If you come to class and you understand what we do here, you're good. So go try the practice. If you have any issues, remember you can email me. We've got that community help document, which isn't really doing much for Math 2. My other classes are blowing up, which is sweet because kids are emailing me for help. But yeah, I want to get you out here by 10:50, so we're 1 minute early, according to me, but let me know when you guys have issues. Otherwise, I will see you on Tuesday, and we'll pick it back up here. If you go look at my slides, there are more. That's what we'll do on Tuesday. So please don't, like, get super motivated and go do everything that I'm going to have us do on Tuesday, because I've got more slides plugged in here. So, like, I've got a lot of stuff planned for next week already. Okay? So that's our exponential models, and... oh, we didn't even get to carbon dating. Okay, well, on Tuesday, here, I'll leave you in anticipation. On Tuesday, we'll actually talk about carbon dating. So,
We just learned about carbon dating in science.
Awesome. Well, how applicable is this? So, wait, do you know how long it takes carbon to have half of what it did before? What's carbon's half-life?
I think 5,380 years or something around that.
You switched a couple numbers and changed one of them. Sorry, Elle, I saw you reach for your notes. It's 5,730. Now, what's crazy, and the reason we use carbon, is it's exact. It's exactly half, like, exactly half. That's what's crazy. All right, I'll let you guys get out of here. Have a great day. Have a great weekend. I will see you on Tuesday. Thank you, guys. You rock. I appreciate your attention. Amar, are you there, dude?